Good day, everyone. Continuing to our following chapter, all silicon semiconductor PD. Silicon has a relatively large indirect band gap, around 1.1 electron volts, corresponding to a cutoff wavelength below 1100 nanometer. As such, silicon is not the most suitable material for PD operating at the telecommunications wavelength compared to the direct band gap 3,5 alloy such as indium gallium arsenide or germanium, which has a smaller band gap. Nevertheless, all silicon PDs have the advantage of monolithic integration with the standard CMOS technology without changing the fabrication process, and hence could significantly reduce the fabrication costs. All silicon PDs operating at telecommunications wavelength based on different physical mechanisms. The first mechanisms are mid-band gap absorption (MBA), surface state absorption (SSA), internal photon emission (IPE), and two-photon absorption (TPA). Knight and his team proposed a silicon all silicon MBA ion photodiode. They are the first team that is introducing this kind of MBA ion photodiode with the defect states introduced by an ion implantation and optimize its performance by post-annealing and exploiting the helium ion as the implantation source, as you can see here. So further adding an external ring resonator, the cavity could this type of cavity resonator could increase the total optical absorption and achieve a complete C and L band coverage. With a modern technology, Gaius and his team were able to reduce the transversal cross-section of waveguide to increase the absorption length and reduce the carrier ring combination, making the performance of these types of MBA PDs comparable with the 3,5 alloy and germanium PDs. They demonstrated a responsivity of 0.5 to 10 ampere per watt at 1550 nanometer wavelength with a 60 volts of bias and a bandwidth larger than 35 gigahertz, and extremely bit error rates with the triple 12 is also reported. Note that besides ion implantation, defect states can also be generated in silicon by roughening the surface using ultrafast laser pulses. All silicon SSAPD. SSAPDs has a similar principle with the MBAPDs that we discussed earlier. The surface states are introduced into the gap of the intrinsic silicon, extending the optical absorption to a longer wavelength. It has been demonstrated that a large number of surface states are present for a clean silicon or germanium surface and vanish as the surface becomes rough or oxidized. By increasing the overlap between the optical mode and waveguide surface using a small conduction arm, Brad Jones and his team built the first SSAPD with ultra-high vacuum environments. They reported a responsivity of 36 milliampere watt at a 1575 nanometer wavelength under 11 volts of bias and a corresponding dot current of 12 microampere. This is the figure shows that they work. Further improvements can be done by the coupling of the SSAPD with an external resonator cavity, as you have known mentioned earlier with the MSMPDs, right? They have application of the implantation and also the cavity resonant cavity integration. So the same thing can be done for all silicon SSAPD. A responsivity of 0.12 milliampere watt at 0 volt bias has been achieved by Chan and his team. Ideally, surface states could have a larger carrier mobilities and less recombination size compared to the bulk defect states at the MBAPDs, resulting in the higher detection speed and larger QE. However, SSA is very sensitive to the silicon surface conditions as well as the external temperature, which requires a delicate fabrication process that hinders mass production. That is unfortunate. Presently, the SSCPD is still in infancy. All silicon IPEPD. IPEPDs rely on the principle that photoexcited electrons in metal can gain energy higher than the Schottky barrier and consequently move into the conduction band of the semiconductor itself like this. So the IPEPDs are widely implemented in infrared imaging systems due to the high switching speed and convenience in fabrication itself. In optical communications, however, it's not favored due to the very low QE, as the photoexcited electrons do not have enough energy or momentum to overcome the Schottky barrier. Elab and his team first proposed an ultra-thin metal films, which are around 2 nanometer, to increase the carrier escape probability due to the of the photos excited electron. So a responsitivity of 250 milliampere watt at 1500 nanometer wavelength was achieved with the trade-off of a total optical absorption. Later, metal porous silicon structures were exploited to improve the QE around 14.4% by increasing the surface to volume ratio itself. Recently, it has been demonstrated that QE can significantly improve by coupling the IPPD with a silicon waveguide. Responsibility of a 4.6 milliampere watt at 1550 was reported at a negative 1 volts of bias. The current is around 3 nanometer and 3 nanoampere, sorry. Although the current IPEPD are limited by small bandwidth around 3 GHz, it still has a high potential for speed communications due to the fast photo emission mechanism. TPAPDs. TPAPDs are based on the nonlinear TPA process shown here. Borges and his team first discovered that an electron can absorb two photons having individual energies below the semiconductor pack approximately at the same time and reach the excited state at the conduction band. Ranges and his team first measured the TPA coefficient, which is around 1.5 cm over kilowatt, using the 1060 nanometer picosecond laser pulse. Later, 0.8 cm gigawatts at 1500 nanometer also was demonstrated at the telecommunication wavelength. Although the nonlinear behavior of the TPA offers the potential in ultra-short laser pulse detection, the small TPA coefficients hinders the application of the optical communications, similar as previous one. And again, coupling with silicon waveguide, um, for the TPAPDs or a high Q resonant cavity can improve the responsivity into 16 milliampere watts at 1500 wavelength nanometer. However, it is still limited by the low detection speed, which is around 0.1 GHz due to the high resistivity of the device. With the continuous progress of this TPA PD development, the weak current of the TPA is significantly amplified in the carrier multiplication process, and the sensitivity is also improved. All silicon CPAPDs are also proposed as profilometers at both 1300 and 1550 nanometer wavelength in detecting ultra-short pulse. At the current stage, the research of TPAPDs is still focused on amplifying the TPA effect to improve the responsivity and also the speed itself. Moving on to mercury cadmium telluride PDs. In terms of material properties, HgClTe is probably the most promising semiconductor for infrared photo detection in a spectrum of 0.7 to 25 micron. This kind of semiconductor has an adjustable bandgap achieved through the tuning of the composition of each element, thereby granting the flexibility of spectral response over a wide infrared spectrum. So This kind of semiconductor PD is a direct bandgap semiconductor with high photon absorption coefficient even for a thin film, which leads to high QE and low noise generation. High lattice mismatch of 0.2% mismatch between HGCDTE tertiary alloy and CD zinc and also telluride substrate ensures the high quality growth. In fact, it is the only material that has nearly the same lattice constants, regardless of the composition of each element. Moderate dielectric permittivity ensures the small device capacitance, and low thermal expansion coefficients ensures the device stability itself. The first and second generations of mercury cadmium telluride PD consist of a linear array of photoconductors and a two-dimensional array of photovoltaic diodes, which are mainly used for thermal imaging at far infrared, larger than 8 micron. Only the third generations of this kind of PD, especially during the development of APD, the potential of this type of PD is in near infrared photodetection is explored. For HGCDTE with a band gap around 0.9 electron volt corresponding to the 1370 wavelength nanometer, the energy required to excite an electron from the valence band to the conduction band is identical to the energy of the excite a carrier from the split of band to the valence band, as you can see here. The value is the same. This property provides the HGCDT-EAPDs a competitive advantage in the asymmetry between the avalanche gain of holes and electrons in multiplication process. An ionization ratio K value of 0.1 or less can be achieved, resulting in an excellent signal-noise ratio and figure of merit better than the indium gallium arsenide and germanium APDs. This kind of at present the HGCDT EAPDs for photo detection of the uh, 1060, 1300 and 1550 nanometer have been fabricated using a liquid phase epitaxy or molecular beam epitaxy MBE. The responsitivity can reach up to 13.1 ampere watt with a currents of 66 nanoampere at 77 volts bias, and the gain can be larger than 100 at room temperature. This is an example of a HGCDTE on a CD zinc and silicon substrate. However, serious problems occurs in mass production due to the weak HG bond. Despite of the outstanding performance, this is a serious problem that they are facing now, including the weak bond, as well as the safety concerns for the highly toxic compounds. Also, at large bulk areas and high operating voltages significantly increase the power consumptions of the device. In addition, the high quality of the HDCDTE is grown on the CD zinc and silicon substrate, which is difficult to integrate with silicon itself. Readout circuit to different thermal expansion coefficients, and also have a 90% of lattice mismatch. And of course, the fabrication costs associated with the types of HGCDTE on the CD zinc substrate itself is also much higher than silicon or even germanium. Future directions: low dimensional materials, graphene and carbon nanotubes. Low-dimensional materials. Low-dimensional materials provide a fascinating ground between molecular and bulk materials. Interesting properties such as excitons, which are often negligible in bulk materials itself, are greatly accentuated in low-dimensional materials. These unique properties, electrical and optical properties, make photo detection promising, even in an extremely small nanostructure that is only one atomic thin layer, for example, like graphene, or even nanometers in two carbon nanotube or three dimensions, for example, constant dots. Graphene. Due to the short interaction length of atomic thin layer, the absorption optical of a single layer graphene is only 2.3% visible in near infrared region. Opacity of the graphene is solely determined by the fine structure constants, which can be defined by E2HC, which results in of its two-dimensional nature and gapless band spectrum. The optical absorption of graphene is nearly linearly proportional to the number of the layers of the graphene itself. The total absorption of the multi-layer graphene can be treated equivalently as a superposition of each individual layer due to the weak van der Waals force between the adjacent layers of the graphene. This property offers a convenient way to tune the absorption of graphene PD without generating so much noise. Other approaches for integrating this graphene with optical structures is including plasmonic structure, optical waveguide, optical cavity, or utilizing the intrinsic plasmonic properties of graphene by patterning the graphene into the nanostructure, or implementing a hybrid material system, for example, polymer nanoparticle controls to increase the light harvesting and facilitate the exciton separation itself. Physical mechanisms in the photodetection of graphene can be categorized into three major categories, which is photoelectric, photothermoelectric, and photobolometric effects. So the first one, photoelectric effect. Graphene typically aligns longitudinally between two electrodes, right? So whereby the photoexcited electrons from exciton are separated and propelled under the external wires to create a photocurrent. For the area away from the metal graphene junction, the photoconductive effect dominates the photoresponse, where the graphene behaves like a conventional semiconductor. On the other hand, for the area beneath, close to the metal graphene junction, the photoresponse is dominated by the photovoltaic effect, PV, where the Fermi energy of graphene is shifted according to the work function of the metal contact, and subsequently a built-in voltage can be established to separate these excitons without using an external bias. Photothermoelectric effect. Due to the strong electron interaction, a photoexcited electron holdback can result in ultra-fast heating of the carriers in graphene. Due to the long transport length for the hot carrier to interact, multiple excitations can further occur by forming inhomogeneous thermoelectric power across the graphene channel. These hot carriers can produce a built-in based on Seebeck effect for a graphene interface junction or a dual gate graphene to generate the photocurrents. Okay, and the third one is the photobolometric effect. The photobolometric effect is associated with the light induced change in the conductance via optical heating instead of the direct photocurrent generation. The temperature dependent conductance can be attributed to the change in both carrier mobility and carrier density. The first graphene PD was reported by Zia and his team, which is a transistor-based PD made out of a single or a double graphene layers, demonstrating an ultra-fast photodetection of 40 GHz. Mueller and his team has developed an interdigitated metal graphene metal structure to break the mirror symmetry of the internal electric field of the conventional FET, which is operated at 1550 nanometer wavelength with a responsivity of 6.1 milliampere watt. Gann and his team coupling with a microcavity resonator with a total absorption of 40% and has a small bandwidth as a trade-off, however. Constantotus and his team covered the graphene layer with a thin film of colloidal QDs to improve the device gain up to an order of magnitude of 8 with a responsivity of 10 to the power 7 ampere over watt, but the response was still limited. Gunn and his team also develop an evanescently coupled graphene waveguide structure, and achieve a responsivity larger than zero point 0.1 ampere over watt. A uniform response between 1450 and 1590 nanometer wavelength and a high speed of 12 gigabit per second. Wang and his team reported a responsivity of graphene C heterostructure structure waveguide PD with a responsivity of 0.13 ampere per watt at a 1.5 volts of bias. Kim and his team reported further improved the responsivity up to 0.4 to 1.0 ampere per watts in a broad spectral range from ultraviolet to near infrared using an all graphene PN junction, vertical junction, such as this. A similar structure was also demonstrated by Liu and his team, show a responsivity of larger than 1 ampere watt from visible to mid-infrared wavelengths at room temperature. CNT. It was first discovered by E.G. and his team in 1991 and are nearly ideal 1D systems with a diameter of a few nanometers and length can be scaled up to centimeters. By controlling the arrangement of the carbon atom structure with respect to their axis, for example, the indices, the direct bandgap semiconductors metal nearly in a ballistic condition. The bandgap of a CNT is inversely proportional to its diameter. So, for example, the bandgap ranges from 0.2 to 1.5 electron volt for 0.8 to 3 nanometer, which allows this kind of CNT for photo detection from ultraviolet to infrared. Besides the tunable bandgap, CNT intrinsically has high absorption coefficient to the power of 4 and 5 in infrared region, which is one order of magnitude larger than the conventional semiconductors. Photoexcitation creates an electron in the conduction band, leaving a hole of valence band. Okay, for the bulk semiconductors, the electron-hole interaction is negligible as they behave like free carriers. But however, for low-dimensional materials, especially specifically for CNTs and quantum dots, the substantial Coulombic interaction due to the strong quantum confinement between the electron and whole quasi-particles binds them into excitons, offering an alternative valley for the charge transfer in low-dimensional materials. Excitons efficiently form in CNT under photoexcitation due to the one-directional confinement and subsequent decay into free electrons and holes. Photocurrents can be this then produced by the external bias or photovoltage created by the built-in near Schottky barrier of p-n junctions. The excitons binding energy is also inversely proportional to the CNT diameter and can be further tuned by adjusting the electric field or even the electric constants of the environment. Carrier multiplication or robust exciton is found to be effective in CNT due to the impact excitation with a Vygotsky response. Thereby, it is a very promising and very attractive for the photo detection application. High performance infrared PDs based on CNTs are usually fabricated using CVD or ME, and the photo detection mechanisms is attributed to the thermal or photo effects. For the thermal effect, the current is generated as a result of the change in conductance due to the temperature change and the light illumination. Saint Antoine and his team demonstrated a thermopile using a single wall CNT as CNT thin film with a detectivity of 2 to the power of 10 to the power of 6, 10 to the power of 6. And Liu and his team showed a bolometer with a higher detectivity around 3.3 to the power of 6 at 1000 to 1300 nanometer wavelength using an MWCNT. These bolometric devices are affected by the surrounding medium made of air or vacuum to improve the sensitivity of the devices. So as you can see here is the unsuspended images using SAM. This here and right is the suspended. Yes. So if we are talking about the multi-wall CNT, so all of this is multi-wall CNT, even in a single one, This is a multi-wall single CNT. This is called multi-wall CNT because the structure of the CNT itself is have a multiple wall, unlike the single wall. Single wall we can directly see the chirality of the CNT. Second one is the photo effect. For the photo effect, the signal is created based on the photoexcited electron. Arnold and his team reported a detectivity 10 to the power of 10 with a 400 until 1500 nanometer of wavelength with a 3 dB bandwidth of 31 megahertz. Liu and his team achieved a detectivity around 2.3 with the P3HT on NCNT heterojunction from 1000 to 1300 nanometer, and the detectivity for this is around 2.3. The device performance can be controlled by the chirality and uniformity of the CNTs. Of course, chirality and uniformity of CNT is important to ensure the quality of the CNT and to control the movement of the electrons of CNT. That's all from me this week. So thank you again, everyone. Take care and have a good day.